Okay, it's a great pleasure to be here. Frank went back 22 years. Let me go back 50 years. Exactly 50 years ago, I was here for the first time. Not in the CIRM. The CIRM did not yet exist, but 200 meters away, the Faculté des Sciences. And there was a 1-month workshop organized by Gérard Debreu and Werner Hildenbrand on the mathematical economics, specifically the mathematical theory of economic equilibrium. So I was at that workshop exactly 50 years ago, which was important for me because one result was that after giving a talk, I got an offer from the economists in Bonn, and I spent 3 years of my life in an economics department. So when mathematical finance started to pop up, I was a priori motivated to have a closer look. And so that started here in Lumini 50 years ago for me. Okay. Now, the title of my talk is Entropy, Energy, and Optimal Couplings on Wiener Space. So, of course, everybody in this room knows what I mean. We take as our basic sample space the space of continuous functions starting at 0. And I use the following notation. The coordinate process defined for little omega being a continuous function starting at 0. Then this coordinate process generates a filtration. And the sigma field F and P will be Wiener measure on omega F, which by poly V can be characterized by the fact that the coordinate process is a square integrable martingale, and the quadratic variation up to time t is equal to t. Okay. Now, let Q be any probability measure on omega F. We are going to discuss 2 questions. The first question is, how far away this Q is from Wiener measure P. And we will discuss this in terms of Wasserstein metrics and in terms of entropy. In the classical sense, and then also on a second level. And more basically, the second question is, what is the impact of entropy bounds formulated with respect to Wiener measure, bounds on Q, but formulated in terms of Wiener measure P, on the structure of Q. Now to discuss more precisely the first part, let us introduce the first Wasserstein metric, defined in terms of the Cameron-Martin space. So that's the space of all continuous functions. which are in fact absolutely continuous. And its derivative, which I denote by a point on the omega, is a function in L2 on 0, 1. And we use the corresponding norm, which is the L2 norm of the derivative if omega belongs to the Cameron-Martin space and plus infinity else. And using this, we can introduce the corresponding Wasserstein metric. So the distance of Q from P is the infimum over all couplings of P and Q, meaning these are omega-valued random variables on some probability space somewhere, such that the first has law P and the second has law Q. And then we take on that probability space in the background the difference in terms of the Cameron-Martin norm. So that's the Wasserstein metric, which we are first going to use. There will be a second one later on. And then also we use the notion of entropy. First in the usual sense, and then we are going to go to another level afterwards. So we define H of Q P. A familiar definition. If Q is absolutely continuous with respect to P and plus infinity else, that's the relative entropy of Q with respect to P. So these are two ways of measuring how far Q departs from P. Now as to 2. The impact of entropy bounds. We can formulate the following theorem. If the relative entropy is finite, then the following happens. Q is the law of a stochastic differential equation. So no other a priori assumptions, just this. More precisely, there exists a map BQ from omega to H. So for each omega, the path is absolutely continuous, and we denote by BQ the derivative. And this will be called the intrinsic drift of Q, such that WQ BQ is a Wiener process under Q, And this will be called the intrinsic Wiener process of Q. And this means that under Q, we can write dW dVQ plus dQ tdt. And that means that W together, also on the probability space with Q, is a weak solution of the stochastic differential equation I have written here. So that's the first part. And the second part is that the relative entropy can then be expressed in terms of the intrinsic drift as expectation under Q of this. Now, the reason I'm giving this talk is that I used this effect in lecture notes in Saint-Flour, not 50 years ago, but in 85. And I discovered that recently, so recently over the last 3 years, this was often cited in the literature on optimal transport. So I started to look at this literature and learned it by doing so to some extent. And then I had one idea of going one step further, which I'm going to sketch later on. In fact, the only thing I added here is the application to entropy. The first part, which follows just from the fact that Q is, if the relative entropy is finite, Q is absolutely continuous with respect to P, is already essentially contained in Lipscher-Cheryaev in their book in 77. Now, why is that of interest? So I won't prove it, but the idea of the proof is very simple. If Q is absolutely continuous with respect to P, we have a density, phi, but we are on Wiener space. So using Ito's representation theorem, phi admits a representation 1 plus a stochastic integral. We apply Ito's formula to the logarithm of that, and we get a representation of phi in the Gilsanov form, and Gilsanov gives us the rest. So that's the idea. Now, why is that of interest? It implies various, or gives a very direct and efficient approach to various inequalities, in particular to log Sobolev, to Talagrand's transport inequality, and other things, Shannon, Stem. And this was pointed out in a paper of Lehec, 2013, and here in this corner, a very interesting recent paper by Eldan and Mikulinza. Okay, now we are going to focus on Talagrand's inequality. And there, we can simply argue as follows. The theorem says that W, together with the intrinsic Wiener process, viewed as a coupling on the probability space with Q, is a coupling of Q and P. The law here is Wiener measure, and under Q, W has the law Q. In fact, it is an adapted coupling, because we also have a filtration, and everything, including the Wiener process. The Wiener process is a Wiener process with respect to this filtration. I won't write down it technically, but the idea is clear. And for this coupling, we have that the cost, the quadratic cost, this is simply BQ. And as we have seen above, which has disappeared, unfortunately, this is 2 times the relative entropy of Q with respect to P. So for this specific coupling, we attain this, but the Wasserstein metric is defined as the infimum of all such couplings. So this yields W square HQP smaller than. And this is Talagon's transport inequality on Wiener space. So that's Talagon 1969, except that Talagon did not talk about Wiener space. He just talked about Gaussian measure on a product space, Euclidean space, but also with infinite dimension. But then he did not point that out. But if you recall the Levi-Ciccielski representation of Brownian motion, this immediately translates into this inequality on Wiener space. So on Wiener space, it was first formulated by Feyel and Ustinel in 2004. And in both cases, the procedure is bottom-up. The first initial step, which is already non-trivial in Talagon, is to prove the inequality on R1. Which involves a subtle trick of integration by parts. Then you prove it step by step on finite Euclidean space. And the step to R infinity is by passing to the limit and using martingale arguments. So, and also Feyel-Ustinel works via finite dimensional approximations. So in these cases, it's bottom up. And here, it's top down. We immediately argue on Wiener space, and then the classical results all follow by projection. So that would be the top-down approach, which, as far as I can see, was first pointed out by Leek. A further remark. As I said here, without really being technical about it, this is an adapted coupling. If you modify the definition of the Wasserstein metric by requiring that all couplings are on a filtered space and are adapted with respect to the filtration, then you obtain the notion of an adapted Wasserstein metric. And in that case, we can show this actually the optimal adapted coupling. So Talleyrand's inequality becomes an equality in that case. And this was first pointed out by LaSalle, 2018, and has recently work of Acciaio et Ali discussed more systematically in the sense what happens if you impose constraints on the couplings. So the constraint of being adapted is one possible constraint. Now, so far I have been expository. I've summarized some development in the literature. Now my question then was, what happens beyond absolute continuity? Now all this works if relative entropy is finite, but that means that Q is absolutely continuous with respect to P. Can we go beyond that? And what I'm going to summarize now are two papers. Which have just appeared in separate Springer volumes, one in honor of Mark Davis, whom we all miss not only as a colleague in probability and mathematical finance, but as a person. And the second is in honor of Fukushima. Fukushima's Beiju. Beiju refers to the 88th birthday, which in Japan is taken more seriously than 80 or 90. You will find they both have just appeared as volumes with Springer, but you also find them on my homepage and on the French platform HAL. Now, what do I do in these papers? The idea is to rescale the definition of entropy. So to do this, let's discretize time. And let's look at the sigma field generated by observing the trajectories along this discrete time. And then we define Hn, the relative entropy of Q with respect to P on the sigma field. So same definition as above, except the density is taken on that sigma field. So relative entropy on this sigma field. And then by a martingale argument, the same which appears in Talleyrand's proof of the infinite dimensional case, tells you that this increase to the global relative entropy which we have used above. Now, if Q is not absolutely continuous with respect to P, this, of course, is infinite. So, therefore, we now rescale entropy and introduce little h QP as the limit, or since it's not immediately clear that the limit exists, we take the limit inferior 2 to the minus n Hn Q P. And this is we call the specific relative entropy. Yeah, this is motivated by the notion of specific relative entropy in statistical mechanics, where we talk about a random field, for example, indexed by the lattice. Now, but Brownian motion can also be viewed as a random field, but the indexing is not by a d-dimensional lattice, but by the binary tree, which comes up in the Lévy-Ciesielski picture. And Hn would be the relative entropy on the first part of the tree up to n. We divide by the number of sites. So this is entropy per site, and we pass to the limit, just as in the theory of Gibbs measures in statistical mechanics. So this notion was introduced by Nina Gantert in her thesis in Bonn, 1901. And there, the main application was to show that this specific relative entropy arises as the rate function for large deviations in the ergodic behavior of quadratic variation. Because quadratic variation, the Lévy-Ciesielski picture, the existence corresponds to a law of large numbers. For the coefficients in the Lévy-Ciesielski representation, and if you look at large deviations for that law of large numbers, you get a rate function, and the rate function is specific relative entropy. Now, here our question is, what is the impact of an entropy bound that this is finite on the structure of Q? Okay. So to begin, we assume that Q is a martingale measure. So that means the coordinate process is a continuous martingale under Q. And so it has a quadratic variation. And the quadratic variation can be viewed as a random measure on the unit interval. So I hope this can be read. I can also write here, yeah. So we take Q in the class of martingale measure, which means that W is a square integrable, automatically continuous martingale under Q. And so we have a quadratic variation, and this can be viewed as a random measure. And its Lebesgue decomposition we denote by in this form with a singular part plus an absolutely continuous part, which we write in this form. Okay. And now we have the following theorem. HQP, the relative entropy, is in general bigger than or equal 1/2 EQ the total mass of the singular part plus integral 0 to 1 f of sigma square dt, where f of x is a function 1/2 x minus 1 minus logarithm x. So something like this, which is plus infinity at 0. And in fact, we have equality in a number of special cases. And just a couple of weeks ago, Beckhoff, Veraguas, and Unterberger last July showed equality if Q is a law of a nice Markovian diffusion. It's not excluded that it's actually always true. I have not yet found a counterexample. Anyway, for our purposes today, it's enough to have the inequality. So, is it already okay? Where are... Okay, thank you. So this can dry. So this theorem shows if the specific relative entropy is finite. Now our question is, what is the impact? Well, we see that then, since the function f of 0 is equal to plus infinity, it must be that this term here is strictly positive Q, almost surely. But that means that we can construct again an intrinsic Wiener process WQT into 0 to t sigma s minus 1 dWs. Easy to check that this is a Wiener process under Q. And so again, we get a coupling. So WQ together with W on omega Q is an adapted coupling of P and Q. We can actually show that it's the optimal adapted coupling, but we don't need that right away. We just want to draw the following conclusion, that W, have we introduced Wn? Not yet. I said it's optimal, but for what cost functional? For Wm of Qp defined as the infimum over couplings. And now, so couplings x wiggle, y wiggle on some probability space, where x wiggle has law p, Wiener measure, and y wiggle has law q. And now we take x wiggle minus y. We both are continuous martingales, so we can get the quadratic variation. We take the quadratic variation up to 1, and we take the square root. So with this definition of Wm, we get the following corollary. So that's in analogy to Talleyrand's inequality. Now one level up beyond absolute continuity. The proof is immediate now. Since this is a coupling, a specific coupling, the infimum is dominated by the cost under this specific coupling. But this can be computed as, well, the first part, the singular part of the quadratic variation under Q, and then plus integral 0 to 1 sigma s minus 1 square ds. But it's easy to see that this here is smaller than or equal to 2 times f of sigma s squared. And then, so we can estimate by replacing, but if you replace, we get the lower bound for our specific relative entropy. And so we get, yeah, there is a 1/2. So if we multiply by 2, we get on the right-hand side this. And so this is dominated by the lower bound of 2hqp. Okay. So this is an analog to Talleyrand's classical transport inequality. Now can we go beyond Qm, the class of martingale measures? And in particular, can this be viewed as an extension, not just as an analog of Talleyrand? To do this, let's introduce the class Q star of all Q in the class of Qs, by which we denote the class of all semi-martingale measures. So the coordinate process is a semi-martingale with Stubb-Meyer decomposition under Q, and such that Q admits an equivalent martingale measure and in fact the minimal in the jargon of joint work with Martin Schweitzer, martingale measure Q star equivalent to Q. And then we define the following Wasserstein metric. W star QP as we take the square of the Cameron-Martin Wasserstein metric between Q and Q star plus the square of the martingale Wasserstein metric between Q star and P and the square root.
What is Q row? What is the set Q row? Q star.
Sorry, I did not understand.
What is the set Q sub row?
Ah, Q, this is supposed to be S. S for semi-martingale. Okay, then we have the following theorem. W star, well, I write it with a square now. QP is dominated by 2 H Q with respect to Q star plus little h Q star with respect to P. Now this yields an extension of Talagan. Talagan is a special case of this because we simply can note if Q is absolutely continuous with respect to P, then the unique equivalent martingale measure is P. H of QP is 0. And this reduces to the Cameron-Martin part. And so this inequality in this special case reduces to Talagrand's transport inequality in its classical, naja, not quite classical, because also on Wiener space. Okay, now beyond QS. And in the title of the talk, which I originally gave, energy appears. I have not talked about energy so far. But in the second paper in the volume in honor of Fukushima's Beichu, this is discussed. For example, what about situations where Q is such that W is a Dirichlet process? Not a semi-martingale, but a Dirichlet process under Q. It was a volume in honor of Fukushima, so I made a point of focusing on Dirichlet. And that means in the decomposition into a local martingale and another process, this other process is not of bounded variation, but the paths have energy 0. And I go even further, but no time to discuss this now, by revisiting the Dupe decomposition and coming up with a continuous Dupe decomposition, which includes Dupe-Meyer and the Fukushima decomposition, representation as a Dirichlet process, as special cases. And yeah, then one can analyze what happens with these inequalities in that more general context. So this is the second of the 2 papers I mentioned. And if it would be a meeting on mathematical finance, I would just mention one thing. but I have no time to really do it now.
Cancellation. As there is one cancellation, you can take 15 more minutes.
Excuse me?
You can take 15 more minutes because the third talk is cancelled. So you
The next talk is
continue.
cancelled.
No, not the next one. The next one is here.
But you can.
The third one.
The third one. Aha, I would have the option to continue for 50 minutes. But I will not take that option, maybe just 5 minutes, because that would make me, could become embarrassing, because I have not prepared. Really. Okay, so just a remark on risk measures on Wiener space. Well, in the first stage of the talk, we had a Wasserstein metric defined in terms of Cameron-Martin space and the classical entropy. We can use both as penalty functions for a risk measure. So we have the entropic risk measure. With some coefficient beta for some random variable on the underlying space, in this case Wiener space. This is the soup of EP minus 1 over beta, or beta, I'm not sure. Q. So that's the entropic risk, which is in a way the most transparent and simple and best understood of all risk measures. We could also, introduce in a similar way and here we take the Wasserstein distance as penalty function. Now this probably is the best understood risk measure. This is the least studied. So I started a little bit, I find it quite interesting. And of course, Talagrand's inequality immediately yields an inequality between these risk measures, because the penalties are depending on the choice of the parameters. But we know that this is square we should take, dominated by 2 times the relative entropy. So this gives moment, I can do this. Okay. Naja. Ja. Superior technique. Now, just one remark. Let's look at the tail field. Now, for Brownian motion, viewed as a random field over the dyadic tree. So this is the information, the asymptotic information which comes up as you refine, go up to beyond the nth level, and then you pass this n. And then obviously, in the Levy-Ciesielski picture, P is simply the product measure on this dyadic tree. So P is 0, 1 on the tail field. This means that for a random variable measurable with respect to the tail field, And the interpretation is this captures the fine structure of Brownian motion paths. And so this will simply be due to the zero-one law, the expectation of the loss given by that functional. And that means this risk measure is not sensitive to risks in the fine structure. For example, volatility would be an example. The volatility is a limit. It corresponds to a law of large numbers on the tree, and so that's tail measurable. Now, if we rescale, taking beta in, and a function, for an f hat, which is measurable with respect to the tail structure. And let's now assume, as is the case with volatility, that this can be written as a limit of functions, and then we define this as the limit of rho beta n fn. This will be sensitive to the tail structure, and the dual representation for that risk measure will be on the tail field the sup over all q, so the usual thing, EQ minus f hat. And what comes now as penalty? 1 over beta h, the specific relative entropy of Q with respect to P. So in this sense, specific relative entropy induces a certain risk measure. And for example, for volatility, of the path, we can compute explicitly what happens. We get that beta is minus 1 over beta log, which is certainly now bigger than 1, as it would be minus, I'm not sure. Anyway, so we can use specific relative entropy to introduce a convex risk measure on Wiener space given by that penalty. We can identify it in this form, and we can look further at properties. The same thing we can do with, if we take the Wasserstein version, where instead of this we take the squared of the Wasserstein distance. But this is just a remark, so I'm not yet sure myself whether really something reasonable can be done with it, but it may be amusing to have a closer look. Okay, and with this I stop. Thanks for your attention.
Thank you very much, Hans. Any questions? Yes.
I have a question. How important is it for the specific, maybe it's a very naive question, sorry, for this specific entropy, how important is it that you take a dyadic decomposition? Did you also take it?
I'm sorry, you must repeat the question. Acoustic, I didn't get it.
So for the specific relative entropy, how important is it that you take a dyadic decomposition? Is this is it very sensitive to the
No, I just no. That's just a personal thing. I find it convenient. No, it can certainly be done with general partitions, and but I have not worked out the details in that case. I'll just stick to one fixed observation procedure along dyadic times. But you're completely right. It's not really dependent on that.
So for different partitions, it would take somehow a refining partition.
Yeah, right.
Come out the same object, or
I have not yet checked it through, but let's see. In the paper I mentioned by just a couple of weeks ago by now what's the name? Bakov, Veraguas. He may have considered in his definition the general formulation.
Yes.
The question is the following, that the inequality which was on the blackboard, this is the upper bound.
Yeah.
And it resembles a bit the inequality for total variation distance in terms of the Hellinger integrals.
Yeah.
And this inequality of Hellinger of total variation is actually two-sided. Is it possible to have here two-sided bound?
No, I'm only aware of the equality in the
No, you see that it is interesting to have
under adapted constraints. Yeah.
And also for the total variation distance, there are some good examples. So if we consider, say, diffusion processes with unit volatility, unit diffusion coefficient, and two drift coefficients, we can have an estimate involving the L2 distance between the drifts. Are here some examples of the same level of specificity for specific models?
Yeah, and that's exactly this paper which I just mentioned. They look at specific explicit diffusion models and verify in that case that we have an equality for the formula of relative entropy.
Okay.
Yeah.
So thank you.
And related to this, I'm just asking, relating to this question, can you prove that the inequality is sharp, like in that paper?
Yes. Not that inequality. That may be inequality, but what is sharp is the extension of Talleyrand's inequality.
This one. I mean, this one. This one is sharp.
Yeah.
Oh, okay.
Well, not always, but if we go back to the previous form, just in terms of specific relative entropy for martingale measures, then it becomes an equality only if the martingale measure
in fact,
is Wiener measure.
You add
Yeah,
up the
that's
two.
because this trivial inequality for the function f, it's sharp, and so.
Okay, thank you.
Yeah.
More questions?
Some questions from the Zoom audience.
But we don't see them.
But they do see us. They see us.
Can you ask them?
Yes, you can.
Das ist immer eine seltsame Situation. Irgendwer in der Welt sieht einem zu und hat keine Ahnung.
Any question from Zoom participants? Who is Zoom, by the way? Any questions?
I am listening, but I don't have questions. Ciao.
Maybe that was Georgia.
There is a question, you mean? There is a question from Zoom?
No.
No.
Okay.
She said hello, but she doesn't have a question.
Okay, so if not, let's thank again Hans for this fantastic talk. Thank you very much.